Chapter 8.6, the three-dimensional Cartesian coordinate system. We'll be learning about the three-dimensional Cartesian coordinates, distances and midpoint formula, the equation of a sphere. We'll be looking at planes and other surfaces, vectors in space, and lines in space, and why this is the analytic geometry of our physical world. You're familiar with the Cartesian coordinate system in the xy plane. We're now going to extend this to three-dimensional space. In the plane, we use two axes and an ordered pair to name points, our x and our y. In space, we use three perpendicular axes and ordered triples to name a point. The axes are labeled x, y, and z. And together, they form what's called a right-handed coordinate plane. So all you lefties out there can voice your displeasure. It's a right-handed world. Sorry about that. So if you hold your right hand in a fist with your fingers curving from the positive x-axis toward the positive y-axis, your thumb points in the direction of the positive z-axis. The points on the axes take the form x0, 0 for a point on the x-axis, 0, y, 0 for a point on the y-axis, and 0, 0, z for a point on the z-axis. So we have a point out here that's parallel to the y-axis. So we have some value for x, the y is 0, and some value for z. The xy plane is divided into quadrants. We have quadrant 1, 2, 3, and 4, moving counterclockwise. The coordinate planes in space divide the space into 8 regions called octants. The origin is 0, 0, 0. And the first octant over here has all the points in space that have 3 positive coordinates. When we are finding distance in 2 dimensions, we subtract the x's and square them, find the difference between the y's and square it, add them together and take the square root. We do the same thing in space, we just add in our third coordinate, or our z. Midpoint, same kind of thing. To find the midpoint of a line, you find the average of the x's and the average of the y's. Now we have a point in space, so we'll find the average of the x's, the averages of the y's, and the average of the z's. So we want to find the distance between the points P, 1, 2, 3, and Q, 4, 5, 6. And then we'll find the midpoint of the line segment PQ. The distance between P and Q will be 1 minus 4 squared plus 2 minus 5 squared plus 3 minus 6 squared, and find the square root of all that, which when reduced is 3 root 3. To find the midpoint, it's 1 plus 4 divided by 2, 2 plus 5 divided by 2, and 3 plus 6 divided by 2. Adding the fractions, we get 5 halves, 7 halves, and 9 halves. And now we're going to have a drawing lesson. We're going to learn to draw three-dimensional objects to look like three-dimensional objects. We need to make the angle between the positive x-axis and the positive y-axis large enough to give the feeling of 3 dimensions. If you make it too small, it's not as clear. We don't get the feeling of three-dimensional as much. In drawing 2 lines, we draw break lines. These 2 lines would be intersecting. Make a small break to show that this line is behind, that CD is behind AB, or make a break in AB to show that AB is behind CD. If we have a plane, a dashed line shows that the line is underneath the plane. A solid line shows the line is above the plane, and notice we have a break in the plane to show that the line is going above it. And without a break, it represents the line directly in the plane. And then drawing spheres. To draw a sphere, first we want to draw the outline. We draw that as a circle. Make it as round a circle as you can get. Then we draw the equator. So draw the front of the equator first. Then we want to match that arc with the upper line, and that will be a dashed line showing that that's hidden. Then we can put in our axes with line breaks and dashed lines. You try it. Try drawing a sphere and drawing XYZ axes. Pause the video while you're showing off your artistic skills. Standard equation of a sphere. If we have a circle centered on the origin, it's x squared plus y squared equals r squared. For a circle, if we shift the center to hk, we would subtract the h from the x and the k from the y. For a sphere, we just add in the third dimension. So a sphere centered on the origin would be x squared plus y squared plus z squared equals r squared. Or if we shift the center, we need to subtract. Find the standard equation of a sphere with center 1, 2, 3 and radius 4. It's simply x minus 1 squared plus y minus 2 squared plus z minus 3 squared equals 16. In 2 dimensions, our first degree equations represent lines. In 3 dimensions, our first degree equations represent planes. Now we're going to look at vectors. In space, just like in the plane, the set of directed line segments or arrows are the vectors. They're used to represent force, displacement, and velocity in 3 dimensions. In space, we use ordered triples to show the vectors. Our 0 vector is 0, 0, 0, and we have our unit vectors. I is 1, 0, 0, j is 0, 1, 0, and k is 0, 0, 1. Moving from 2-dimensional to 3-dimensional, many of the properties of vectors can be extended. When we're adding, we add our 3 components. Subtracting, we add the 3. Finding the magnitude, vector 1, the square root of vector 1 squared plus vector 2 squared plus vector 3 squared. The dot product is the sum of the product of the x's, the y's, and the z's. And the unit vector is the vector divided by the magnitude of the vector. And equations for lines in space. We're going to find the equations for lines in space and compare it to the parametric forms. If we use the standard unit vector I, j, and k, and we want to write a vector equation for the line containing the points A, which is -5, 6, 0, and B, 7, -2, -4, and then we're going to compare it to the parametric equations for the line. So going from point A to point B, we have a vector, and it's just like finding it in 2-dimensional when we have the head minus tails. It's just that we have a third component to figure in. The head is the B, the tail is the A. So head minus tail, 7 minus -5, -2 minus 6, and -4 minus 0 gives us the vector 12, -8, -4. Then we find the vector going from the origin to A, and the line that we're looking for is going to be vector going from the origin to the A plus some constant times our vector AB, which is 12, -8, -4. So that vector xyz is going to be our original A, the vector -5, 6, 0. That's from the origin to A, plus some number times the vector AB. which is 12, negative 8, negative 4. So if we add those together using distributive property here, and then adding them, we get negative 5 plus 12t for the x, 6 minus 8t for the y, and negative 4t for the z. This can also be written as negative 5 plus 12t I plus 6 minus 8t j minus 4t k. The parametric equations for this are x equals negative 5 plus 12t, y equals 6 minus 8t, and z equals negative 4t. Now try this one. Write a vector equation for the line passing through the points A, negative 1, 0, 3, and B, 3, negative 2, 4, and compare it to the parametric equations. And always remember, label your axes.